Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with number 13 in chapter, with number 50 in chapter 13 in your OER University Physics text. And if you read it, this problem is about Halley's Comet. And there's a couple distances given in the problem that are given in AUs. And AU is an astronomical unit. It's the distance from the sun to the earth. And the first thing we want to do with this problem is draw a picture, just like most good problems. So Halley's Comet is orbiting around our sun. So I'll start this with kind of a picture of maybe, here's our sun, all happy. And then the comet itself is orbiting in kind of an elliptical path. So the elliptical path of that comet might look something like this. So here's a picture of comet way out here, which I'm going to go ahead and call position 1. And here's a picture of the comet way out here. I'm going to call that picture 2. Now, this distance right here is given in the problem, and that distance is, let's see, it says 0.586 AUs. I'll go ahead and just write that, 0.586 AUs. I could convert that to meters if I wanted to, but I'm not going to. I don't think we're going to need to in this problem. Or we may or may not, I don't know yet. Second distance here, 17.8 AUs. Now again, this AU stands for astronomical units. If you need to convert that to meters, what you do is you look up the distance from the sun to the earth in kilometers or meters. And that distance is equal to 1 AU. So that's how you would convert these to meters or kilometers here. So as Halley's Comet goes around the sun like this in this orbit, there's three approaches we could take to analyze it. First of all, let's talk about Newton's second law. We could draw a free body. And let me draw a free body at kind of an arbitrary location here. Let's say it's right here. If we draw a free body diagram, it's going to look something like this. We're going to have the gravitational force. And when you apply Newton's second law to this, you're going to have that the gravitational force is equal to the acceleration, mv squared over r. Now, you'll notice, though, that the r is not constant in this problem. This is not a circular motion problem. You can still apply Newton's laws to this in this elliptical path, and what you could do is you could use an average radius. So for this r, you would average these two, and then you would end up with basically an average speed. And you can apply that to get the period, or to write any equations that will be for one complete cycle. You can't actually do that to get equations good for instances in time along here, but you can do it for complete orbits. So I wanted to chat about how you might attack this, but I don't think this is going to be the best way to work this problem. The other things we can do, looking at this system, this force that I drew on this comet here, if I define my system like this, that's an internal force, because this force that is acting this way on the comet acts this way on the sun. Now this is pretty well an insignificant force as far as the sun is concerned, but the important thing to realize is as long as we consider this our system, that's an internal force. So, and that means that both linear and angular momentum for this system is conserved. There's no external torque acting on this system. Because there's no external torque, we can do this. We can take the angular momentum at position 1, which is equal to R1 times mv, and set it equal to the angular momentum here at position 2, R2 mv2. Now technically, if I'm including the sun here, the sun has an angular momentum because it's rotating on its axis. But it's the same on both sides and really doesn't need to be considered here. So we can basically just look at the angular momentum here, set it equal to the angular momentum here, and that's going to give us some sort of relationship here for these velocities. We can also do an energy consideration. If I write out an equation for the energy at position 1, we're going to have a PE1 plus KE1. Right, remember the work energy theorem, plus work from 1 to 2 equals PE2 plus KE2. There are no external forces acting on the system doing work. So my PE1 term will look like this, minus g mass of the sun, mass of the comet, over, I'll say R1, with this being R1. However, you'd want to convert it to meters for putting into this equation. There's a kinetic energy term, 1/2 mv1 squared, equals, then you write out similar terms on the right-hand side. These two equations should be enough to answer whatever questions are asked for in this problem. That should be enough to get it going. So, again, start the problem with a decent picture of what's going on, which I've done here. And then you have to decide what type of equations to write. You could use a Newton's second law analysis, use the average radius for these, but again, that equation is only good for like averaged over one cycle. So it would be good if you're given kind of an orbital period or looking for an orbital period or something like that. You can also write angular momentum conservation because there's no external torque acting on this system, and you can also basically write an energy conservation because there's no forces doing work in this problem. This force technically, one could argue, does work as this object goes from 1 to 2, but that's taken into account with these potential energy terms. So that should be enough to get this problem well underway. Hope that you do well on it. Have a great day.